Have you ever stopped to think about the rules that run, well, everything? From a car just driving down the street to a spacecraft that's coasting through the cosmos. See, these aren't rules we humans invented, they're rules we discovered. Physics, really, is our quest to understand the fundamental laws of the universe, and our journey starts right now.
And that's what's so beautiful about it, isn't it? The universe is already humming along with this perfect set of principles. Our job, as curious people, is just to try and decode that magnificent system. So in this explainer, we're going to start decoding the very first chapter, the language of motion. So how do we learn this new language? Well, we're going to start with something we all know, a simple car trip. We'll use this everyday journey to build the basic vocabulary we need to describe how anything and everything moves.
Okay, so check this out. This slide shows the difference between the journey you actually took and the journey you could have taken. Imagine you drove 150 kilometers on all these winding roads, like the path on the left. That's your distance. It's what your car's odometer would read. But displacement, on the right, is different. It doesn't care about the scenic route. It's just the straight line from where you started to where you ended. It only cares that you ended up, say, 100 kilometers north of where you began. Now, let's build on that idea. We all get speed. It's just how fast you're going. It's what the speedometer on your dashboard shows you. Simple, right? But in physics, we often care a whole lot more about velocity. Think of velocity as speed with a GPS. It's not just how fast you're going, but also in what direction, just like that compass on the right. So you're not just going 100 kilometers per hour, you're going 100 kilometers per hour north. It's way more specific, and as you're about to see, that really matters.
And here is a perfect example of why that distinction is so crucial. Let's say you drive 50 kilometers out, then realize you forgot your friend, and you have to drive almost all the way back. You've traveled a huge distance, 100 kilometers, and your average speed was a pretty decent 50 kilometers per hour. But look at your displacement. You only ended up 5 kilometers from where you started, so your average velocity was a measly 2.5 kilometers per hour north. You burned a lot of gas, but you didn't actually get very far.
Okay, so we can describe motion. But in the real world, things don't just travel at the same speed in the same direction forever. They speed up, they slow down, they turn corners. So let's look at the engine of all that change, acceleration, and the force that causes it.
Think about what happens when you hit the gas pedal. As this chart shows, a sporty car might take only 10 seconds to get up to 60 kilometers per hour, while a big, heavy truck takes a full 30 seconds. Now, they both get to the same final speed, but the car gets there a whole lot faster. That difference, that measure of how quickly they change their speed, is acceleration.
So what is acceleration, officially? It's simply the rate of change of velocity. For our car, we'd take its final velocity of 60, subtract its starting velocity of 0, and divide it by the 10 seconds it took. What that tells us is that its velocity was increasing by 6 kilometers per hour times every single second. That's what acceleration is all about. It's a measure of how fast your velocity is changing.
And you know this feeling. We've all felt it. When a car slams on the gas, you feel a force literally pushing you back into your seat. When it takes a sharp right turn, you feel pushed to the left. That physical sensation, that push or pull, is our first real introduction to the idea of force. And nobody explained force better than Isaac Newton. You could say Newton gave us the official rule book for motion. 3 simple but unbelievably powerful laws that explain how and why everything moves, from a tiny apple falling from a tree to the planets orbiting the sun. His first law is the law of inertia. And you can think of it like this. Objects are fundamentally, well, kind of lazy. They just want to keep doing whatever they're already doing. If something is sitting still, it'll stay still. If it's moving, it's going to keep moving at the exact same speed in the exact same direction, unless some outside force comes along and messes things up. And you see this everywhere. When a car slams on the brakes, your body wants to keep moving forward. That's inertia. A fan keeps spinning for a bit even after you cut the power. But the most incredible example? The Voyager spacecraft. It's just coasting through deep space right now, with almost no external forces out there like gravity or air to stop it. It just keeps going and going and going. Now, to really get to the next law, we have to clear up something that trips a lot of people up: the difference between mass and weight. Mass is the amount of stuff you're made of. It's constant. Your mass is the same here on Earth as it would be on the moon. Weight, on the other hand, is a force. It's the force of gravity pulling on all that mass. And since the moon's gravity is much weaker, you would weigh a lot less there, even though the amount of you hasn't changed one bit. And that leads us to this. Possibly the most famous equation in all of physics. Force equals mass times acceleration. Just 3 letters that completely changed how we see the world.
So, what does it really mean? It tells us that if you want to accelerate something, change its velocity, you've got to apply a force. And the more mass something has, the more force you're going to need to get the same acceleration. It's exactly why it's way easier to push a shopping cart than it is to push a car. The car has so much more mass, so it requires a whole lot more force to get it moving.
Newton's third and final law is just as mind-blowing. It basically says that forces never show up alone, they always come in pairs. For every single action, there is an equal and opposite reaction.
Think about something as simple as jumping. You can't just float up into the air, right? First, you have to do something, an action. Your feet push down hard on the ground. The reaction is that the ground pushes back up on you with that exact same force, and that's what launches you into the air. You push on the earth, and the earth pushes right back on you. Okay, we have our 3 laws. Now, for the grand finale, let's put them all together and watch them work in perfect harmony in one of the most incredible things humanity has ever achieved, a rocket launch. At liftoff, it's all about Newton's third law. The rocket throws hot gas down with incredible force. That's the action. The equal and opposite reaction is all that gas pushing the massive rocket up. As it climbs, Newton's second law takes over. That massive force from the engines is accelerating the rocket's huge mass toward the sky. And finally, once it reaches space and the engines cut out, Newton's first law, the law of inertia, takes the controls. With no forces to slow it down, that rocket will just coast in a straight line pretty much forever. So from a simple car trip all the way to a rocket launch, these laws are absolutely everywhere. That little sting you feel in your foot when you kick a ball, that's the ball kicking you back. So the next time you jump or drive your car or even just watch something fall, think about these invisible rules. Where else in your everyday life can you spot Newton's hidden laws secretly running the show?